Hello students, welcome to the EPG Pathsala. I am Professor D. Murugan, former head of the department, Center of Advanced Study in Crystallography and Biophysics, University of Madras, Gindi campus, Chennai, and I am at present working there as the University Grants Commission Basic Scientific Research Faculty. Today, we are going to discuss about the module dealing with molecular modeling and drug design and the paper biocrystallography. So, students, let us see what we are going to learn in this module. First, I am going to introduce you all to molecular modeling. Then I am going to talk to you about molecular graphics and also the basics of computational quantum mechanics. We are going to deal with density functional theory, empirical force field model, and also about exploring the energy surface. We are also going to deal with simulation methods using computers, which are also called molecular dynamics, in silico molecular dynamic simulation methods, and quantitative structure activity relationships called QSIR. Molecular modeling deals with the ways to mimic the behaviors of molecules and molecular systems. It is invariably associated with computer modeling and has been revolutionized by computational techniques to the extent that most of the calculations could not be performed without the use of a computer, and thus computers have extended the range of models that can be considered and the systems to which they can be applied. The CPK model, developed by Corey, Pauling, and Colton, is the space-filling model used by most of the chemists to enable three-dimensional representations of the structures of molecules to be constructed. These are useful both in teaching and also in research. Molecular modeling is also concerned with quantum mechanics, for which foundations were laid many years before the advent of computers. Computational chemistry is very much involved in molecular modeling, wherein quantum mechanics, molecular mechanics, energy minimizations, simulations, conformational analysis, and other computer-related methods for understanding and predicting the behavior of molecular systems have their roles. Computer graphics is also very much associated with molecular modeling. Bioinformatics uses molecular informatics and chemoinformatics, which deal with manipulation of information about molecules by retrieving the stored information in the computer. The chemists are now relieved of the burden of synthesizing thousands of compounds to obtain the lead molecules. They have to now use gas screening methods in bioinformatics tools to synthesize potential leads after ruling out thousands of compounds when they do not satisfy the rules in modeling and docking. So here we talk about the Lipinski's rule of 5 and so on. Molecular informatics has also gained substantial amount of information through automated sequencing machines being used to determine the human genome. In molecular modeling, Born-Oppenheimer approximation enabling the separation of electronic and nuclear motions is used. Changes in the energy of a system cause movements on a multi-dimensional surface called the energy surface. Let us understand what we mean by molecular graphics. The interaction between molecular graphics and the underlying theoretical methods has enhanced the accessibility of molecular modeling methods to assist in the analysis and interpretation of these calculations, and this is known as computer graphics. You can visualize what's happening. Raster devices have superseded vector devices in molecular modeling. CPK models are generally used in molecular graphics. Using depth queuing, the impression of three-dimensional structure of an object can be felt in the two-dimensional computer screen. This is very well understood in the modeling of molecular structures, as I have earlier seen. The computer graphics program provides facilities like translation, rotation, and zooming towards or away from the viewers of the models. Proteins are commonly represented using ribbon models. Non-covalent interactions between two or more molecules are often facilitated by the van der Waals surface of the molecule. The formula of Connelly and Richmond have been used for calculating the exact or approximate values of the surface area. Many software programs are used by molecular modelers, starting from a single task program to highly complex packages. Ab initio quantum mechanical calculations can be carried out using the Gaussian programs, the semi-empirical quantum mechanics calculation using MOPAC or AMPAC programs, and the molecular mechanics calculation using MM2 programs. Let us learn now some basics of computational quantum mechanics. Since quantum mechanics explicitly represents the electrons in calculations and also to derive the properties that depend upon electronic distribution leading to chemical reactions, these methods were implemented using computers, and computational quantum mechanics was used by chemists. Huckel theory, valence bond theory, and density theory are all incorporated in the computational quantum mechanics, and the computers do a lot of work in these areas in the fastest way. Hartree-Fock equations can now be applied to molecular systems using computational methods. Molecular properties can also be calculated using ab initio quantum mechanics. Using the partitioning of electron density, bond order, electrostatic potential, and thermodynamics, structural properties can be studied using computational methods. By incorporating parameters derived from experimental data, some approximate methods can now calculate certain properties more accurately than the highest level of ab initio methods. Now let us learn something about the density functional theory, which is also abbreviated as DFT. DFT is an approach to the electronic structure of atoms and molecules. While Hartree-Fock theory calculates the full electron wave function, DFT calculates the total electronic energy and overall electronic distribution, as there is a relationship between these two energies. DFT methods using the radiant correction can give results for a wide variety of properties that are in some cases superior to ab initio calculations. For the optimization of molecular geometries, DFT methods are applied. Let us look into the empirical force field model in molecular mechanics. MM denotes molecular mechanics. Quantum mechanical methods cannot tackle problems of too large dimensions, whereas molecular modeling can be used to tackle these problems. The force field being used in molecular mechanics can provide answers which are as accurate as even the highest level quantum mechanical calculation in a fraction of computer time. The only limitation of molecular mechanics is that it cannot provide properties that depend upon the electron distribution of a molecule. This is because molecular mechanics ignores the electronic motions and calculates energy of a system based on nuclear positions only. The success of molecular mechanics calculations on the systems containing significant number of atoms and its working are due to the validity of several assumptions like Born-Oppenmeier approximation. The parameters developed from data of small molecules in the force fields can be used to study much larger molecules such as polymers also. Molecular mechanics force fields include contributions from bond stretching, angle bending, and torsional terms. Improper torsions and out-of-plane bending motions have also been incorporated, and also the cross terms in the force fields reflecting coupling between the internal coordinates. The non-bonded terms in a force field comprising electrostatic interactions and van der Waals interaction are also included in the force fields. Efficient rapid methods are used for calculating atomic charges, and distributed multipoles are used to represent the anisotropy of a molecular charge distribution. Aromatic interactions, polarization effect, and solvent dielectric models are incorporated. In van der Waals interaction, the dispersive interactions and exchange forces are also included. While modeling van der Waals interaction, Lennard-Jones 12-6 function is used. For handling many body terms in the potential, efficient pair potential formula is used. The grid is used for finding energetically favorable regions in protein binding sites by using a direction dependent 6-4 function in hydrogen bond calculation as suggested by Goodford in 1985. Molecular mechanics force fields are introduced for the simulation of liquid waters. To overcome the minor drawbacks of united atom force fields used in the calculations on proteins, Tuxwade anisotropic potential is being used in present times in molecular mechanics. Molecular mechanics can be used to calculate thermodynamic properties like heats of formation, which are comparable with experimental results. Strange energy can also be calculated using molecular mechanics programs along with steric energy. Molecular mechanics force fields may be used to determine a variety of structure-related properties, and parameterization data should be chosen accordingly. The optimized parameters for liquid simulation developed by Jorgensen and Tidode-Reeves called OPLS, these parameters are applied to reproduce thermodynamic properties using computer simulation techniques. Quantum mechanical calculations are increasingly used for the parameterization of molecular mechanics force fields. Sometimes scientists use AMBER. By this we mean assisted model building with energy refinement force field for the calculations. AMBER force field is designed for calculations on proteins and nucleic acids. A good general force field can often perform out a poor specific force field. There are special force fields for inorganic molecules, solid-state systems, and also for metals and semiconductors. Let us consider how to explore the energy surface and also how to do the energy minimization. The way in which the energy varies with the coordinates is often called the potential energy surface or the hypersurface. Every system wants to attain the minimum energy. For a system with n atoms, the energy is a function of 3n minus 6 internal or 3n Cartesian coordinates. In molecular modeling, one is interested in minimum points on the energy surface. When there are a very large number of minima on the energy surface, the minimum with the very lowest energy is known as global energy minimum. Minimization algorithms is used to identify those geometries of the system that correspond to minimum points. The highest point on the pathway between two minima is known as the saddle point, where the arrangements of the atoms are in the transition section. Both minima and saddle points are stationary points on the energy surface, where the first derivative of the energy function is 0 with respect to all the coordinates. Minimization algorithms can be classified into two groups. One is the one which use derivatives of the energy with respect to coordinates, and the second is the one which do not use these. The first one of these is very useful. There are many factors to be taken care of when choosing the most appropriate algorithm. Most minimization algorithms can only go downhill on the energy surface, and hence they can only locate the minimum that is nearest to the starting point. The input to a minimization program consists of a set of initial coordinates for the system coming from a variety of sources. If it is coming from X-ray crystallographic study, behavior of that protein in water can be studied by immersing it in a solvent bath where the coordinates of the solvent molecules will be obtained from a Monte Carlo or molecular dynamics simulation. The abbreviation is MC. One uses the simplest method for the energy minimization when the initial configuration of the system is very high in energy, as this takes a lot of computer time. Two first-order minimization algorithms that are frequently used in the molecular modeling are the methods of steepest descent and the conjugate gradient methods, out of which method of steepest descent is used first, then conjugate gradient method is used next. Both these methods gradually change the coordinates of the system as they move the system closer and closer to the minimum point. The conjugate gradient method produces the set of directions which do not show the oscillated behavior of the steepest descent in narrow valleys. While in the steepest descent method, both the gradients and the direction of successive steps are orthogonal, the gradients at each point are orthogonal, but the directions are conjugates in case of conjugate gradients. A set of conjugate directions has a property that for a quadratic function of m variables, m steps are sufficient to reach the minimum. The Newton-Raphson method is a second derivative method to locate the minimum. The choice of minimization algorithm depends on how many factors like the storage and computation requirements, the relative speeds with which the calculations can be performed, the availability of analytical derivatives, and the robustness of the method. For the molecular mechanics calculations of a small molecule, the Newton-Raphson method may be used, provided another robust method such as the simplex or steepest descent is applied to perform a few steps of minimization. Docking results show that the steepest descent method can actually be superior to conjugate gradient when the starting structure is some way from the minimum. However, conjugate gradient is much better once the initial strain has been removed. For terminating the minimization calculations, once the value is close to the minimum, there should be some means to decide. The simple strategy is to monitor the energy from one iteration to the next and to stop when the difference in energy between successive steps falls below a threshold. Alternate method is to monitor the change in coordinates and to stop when the difference between successive configuration is sufficiently small. The last method is to calculate the root mean square gradient, which is obtained by adding the squares of the gradients of the energy with respect to the coordinates and dividing by the number of coordinates and taking the square roots. Let us now look into the applications of energy minimization. Energy minimization is an integral part of techniques such as conformational search procedures and is very widely used in molecular modeling. Energy minimization is also used to prepare a system for other type of calculations. The techniques that are specifically associated with energy minimization methods are normal mode analysis and the study of intermolecular processes. Computer simulation methods enable us to study the behavior of macromolecules. They also help us to study complex processes to predict their properties through the use of the techniques that consider small replications of the macroscopic systems with manageable numbers of atoms or molecules. Simulation techniques also enable the time-dependent behavior of atomic and molecular systems to be determined and also provide a detailed picture of the way in which a system changes from one conformation or configuration to another. In the determination of protein structures from X-ray crystallography, simulation techniques are widely used. Time average is a value one measures experimentally as an average over the time of the measurement. Let us go in details the in silico molecular dynamic simulation methods. In the Monte Carlo method, which we abbreviate as MC method, random configurations are generated and a special set of criteria are used for deciding whether to accept each new configuration or not. This is based on the probability of obtaining a given configuration which is equal to its Boltzmann factor and also depends on the potential energy function. States with low energy are generated with higher probability than configurations with higher energy. In some cases, new configurations may also be obtained by moving several atoms or molecules or rotating about one or more bonds. If energy of the new configuration is lower than the energy of the predecessor, then only the new configuration is accepted. The molecular dynamics or the MD simulation and MC simulation methods differ in many ways. The main difference is that MD provides information about the time dependence of the properties of the system, whereas there is no temporal relationship between successive MC configurations. The outcome of each trial move in MC simulation depends only on its immediate predecessor, whereas in MD, it is possible to predict the configuration of the system at any time in the future or at any time in the past. This is done by Bernoulli's algorithm. MD has the kinetic energy contribution to the total energy, whereas in the MC simulation, the total energy is determined directly from the potential energy function. MD is a constant NVE ensemble, where N is the constant number of particles, V is the volume, and E is the energy, whereas the traditional MC simulation samples from the canonical ensemble, NVT ensemble, where T is the temperature. Simulation methods predict the thermodynamic properties of system for which there is no experimental data, or system for which the experimental data is difficult or impossible to obtain. Simulations can also provide structural information about the conformational changes in molecules and the distribution of molecules in a system. Energy, heat capacity, and pressure can be calculated in a canonical ensemble in MC simulation when the total temperature is constant. In the microcanonical ensemble in MD simulation, the temperature will fluctuate. For describing the structure of a liquid system, radial distribution functions are used and thermodynamic properties can be calculated. Computer simulation uses phase space, and for a system containing n atoms, 3n positions and 3n momenta define a point in the 6n dimensional phase space, and an ensemble is a collection of points in this phase space. The mechanical properties such as the internal energy, the pressure, and heat capacity can be routinely obtained from MC or MD simulations. These simulations preferentially sample the low energy regions of phase space. Coming to the practical aspects of computer simulation, one has to choose the initial configuration close to the state which is desired to be simulated. Boundaries and boundary effects are crucial to simulation methods. In MD simulation, Bernoulli algorithm uses the positions and accelerations at time t and the position from the previous step or at a time t minus delta t to calculate new positions or at a time t plus delta t and also the velocity. MD is traditionally performed in the constant NVE or NVEP ensemble. Solvent effects can also be incorporated in MD simulation by means of potential of mean force called PMF. Conformational changes can usually be visualized from MD simulations. Lipid bilayers can be simulated due to their biological importance in MD simulations. Once protein structures are predicted from sequences, say using modular program, this model should be subjected to MD simulation, and depending on the problems, simulation in water medium or lipid medium is essential. Then only docking could be carried out with this model. Each system takes its own time for getting stabilized during the simulation. Majority of systems stabilize between 20 to 50 nanoseconds. Now let us go in detail about molecular docking. For doing docking calculations, free softwares like Autodock is available. When you say docking, two molecules are considered. Usually in the field of drug design, a macromolecule and a ligand molecule are considered. Now protein and protein can also be docked, that is protein-protein docking, and so on. In general, commercial softwares like GOLD, released by International Crystallography, and GLIDE, for example, just to take a commercial package, GLIDE, are also available. For the macromolecular structures, hydrogen atoms are not located in X-ray crystallography with such a determination because it is so light, and also considering thousands of atoms to be determined, so hydrogen atoms location is not possible unless you have atomic resolution or subatomic resolution data. But hundreds of hydrogen atoms exist in protein structure, and hence they cannot be neglected, no? So these hydrogen has to be fixed. So commercial softwares add these hydrogen atoms, which is known as protein preparation. Ligands are also prepared. Protein and ligand preparation modules avoid steric clashes between the atoms. If the active site of a macromolecule is already known, docking could be straight away done at the active site of the protein. You just place the ligand at the active site of the protein, the energy minimizes them together. If not, several modules are available to predict the active site of the target protein. Before carrying out the docking study, the target and the ligand molecule should be energy minimized separately. Upon the binding of a ligand at the active site, conformational changes may occur at the site of binding, and hence the amino acid residues at the active site pocket have to be flexible. But if the flexibility has to be considered, then there are several rotatable bonds for which energy calculations have to be carried out while a ligand binds at the site, and many portions of ligand molecules have to be considered. This involves lot of computation time. Hence, flexibility is considered only for the ligand molecule, and the receptor site is considered to be rigid. You see the criteria from the scores and energy values. Selection can be made regarding the binding of ligand from many to few. Thereafter, the receptor can also be considered flexible along with that of the ligand, and this is known as induced fit docking. This concept has worked out well in docking studies, as the theoretical results match about 90% to the experimental results. Depending upon the size of the macromolecular target, the commercial software takes about few hours to do the induced fit docking compared to nearly an hour to do rigid docking while screening hundreds of compounds. Best ligand with good inhibition can be selected by analyzing the score, energy and active site hydrogen bonds and hydrophobic interactions. For the initial filtering of the ligand, Lipinski's rule of 5 can be used, namely, the molecular weight of a ligand molecule cannot be greater than 500 Dalton, there cannot be more than 5 hydrogen bond donors, there cannot be more than 10 hydrogen bond acceptors, logarithm of the partition coefficient log P should not be greater than 5 or less than -2. Most of the prevailing drugs obey Lipinski's rule of 5 to the highest percentage. That is why in designing new drugs, we just want to check these rules. This shows the MER kinase docking results. The table tells you the results for the core crystal. Already in the protein data bank, the protein is bound with some ligand molecule, usually a drug molecule, and the second row tells what is the compound we use as a ligand. If you look at the second column, this gives the docking score, then third column gives you the glide energy, then fourth gives you the interaction. Between the ligand and active site amino acids, some of the atoms can be donors, some of the atoms can be acceptors. A donor atom is the one with which hydrogen is directly bonded. And these donors and acceptors have hydrogen bonds. Whenever the distance between donor and acceptor is between 2.3 to 3.4 angstrom, we call it as a hydrogen bond. So that's listed in the last column. The right hand side in each set of figures shows the leak plot showing the hydrophobic interactions. The residues are shown like eyebrow symbols, no? The hydrogen bonds are marked with dashed lines. What is QSAR? By QSAR we mean quantitative structure activity or structure property relationship. This relates numerical properties of the molecular structure to its activity by a mathematical model. The in vivo activity of a molecule depends on many factors, and the structure activity study can help to decide which features of a molecule give rise to its overall activity. Hence, developed equations which relate the biological activity to the electronic characteristics and hydrophobicity of the molecules. These are called physicochemical properties. If C denotes the concentration of the compound to produce the standard response in a given time, log P, the logarithm of partition coefficient of the compound between 1 octanol and water, as a suitable measure of relative hydrophobicity, sigma the Hammett substituent parameter, and K1 to K4 as constant, then the quantitative structure relation equation is logarithm of 1 over C equals K1 times log P minus K2 times log P whole square plus K3 times sigma plus K4 as given in 27.1 equation. So, it is an algebraic equation where the right hand side consists of the physicochemical properties with proper coefficient and left hand side is the activity. The property chosen for the inclusion in the QSR equation should be as uncorrelated with each other as possible. Many programs are now available for doing QSIR, and 3D QSIR is also possible now. QSIR are often interpreted in terms of specific interaction in the macromolecular target. This just shows the native or opposed structure of sphingosine kinase 1A. If you look at the second figure, 27.1b, same is shown along with an inhibitor. The PDB entry is given here. So you can just see the inhibitor bound at the right hand bottom. So what I am telling you is, if you look at these figures A and B, in B you can find easily the change in conformation, the two helices, how they are connected in figure A in the right hand side, and look at those helices when a ligand is bound. This is known as conformational change due to binding of a ligand. This shows left hand side a superposition of bound and unbound sphingosine kinase in different colors. The blue color denotes apoform, the green denotes the inhibitor bound. So in the inhibitor bound region, you just see the deviations. In the figure B, ligand showing interaction with the active site residues. This is around 4 angstrom distance. This is the output of the molecular dynamics simulation. Usually in any molecular dynamics simulation, we used to draw these graphs. Figure 27.3 shows two graphs. The upper one shows the root mean square standard deviation and the radius of gyration. Lower one is the radius of gyration plot of the apoprotein, black, native, and the inhibitor bound in red for again sphingosine kinase 1A. If you look at that, the flexibility is restrained in case of red. So when the inhibitor is bound, flexibility is not there, it is arrested. That is what is expected. The right hand side figure shows the root mean square fluctuation, RMSF plot of apoprotein and inhibitor bound one shown as red. See, red is coming down, no, fluctuation is less, black is going up. Fluctuations are more in the unbound state and it is coming down during the bound state. I am just showing an example of the influenza virus related macromolecule, neuraminidase H1N1. Here we have superposed the wild type and the mutant structures. The residue labeled for wild type is red and the mutant is blue. The wild type, we have the histidine, and mutant we have tyrosine. The left hand side top you just see, because of mutation, look at the conformation, how the histidine has come from the right hand side moves to left hand side of the tyrosine. The effect of this is to influence the conformation of glutamic acid, which is near to the original histidine. Then you can clearly see during mutation how the glutamic acid conformation changes. So this shows the binding of the anti-influenza drug oseltamivir with the wild type, and the right hand side shows the same binding of oseltamivir when the residue tyrosine histidine is mutated to tyrosine. So you can clearly see when the histidine in the left hand side is mutated to tyrosine as in the right hand side, the glutamic acid 270 conformation is changed a lot between left hand side and right hand side. The effect of this is to push the oseltamivir binding down, and oseltamivir will lose some of the hydrogen bonding interaction. That's why people say that this is the cause for the drug resistance in the influenza virus for oseltamivir, whereas the zanavimab behaves good with hydrogen bonds before mutation and also after mutation. So students, let us summarize what we have learnt in this module. The basics of molecular modeling are all explained to you in detail in this module. Advancements in computer graphics, which is an important advancement in the visualization of the space filling model to portray a three-dimensional image, are highlighted in this module. DFT calculation used to calculate total electronic energy is explained and compared with other energy approximation methods. MM, QMM, OPLS and other methods are given with their uses and applications in different molecular modeling methods. Induced fit docking and the commercial and academically available packages are also explained along with quantitative structure activity relations called QSIR, which play an important role in the field of drug designing. Thank you.